There's something lurking in the depths of space that shouldn't exist. A cosmic rebel so defiant, it's tearing up the rulebook of the universe. Picture this, a black hole, already one of the most mysterious and terrifying forces in nature. But this one isn't playing by the rules. It refuses to spin, and that's like finding a car without wheels or a clock that doesn't tick. It shouldn't be possible, yet here it is, staring back at us from the void, challenging everything Einstein's theory of relativity told us about how black holes behave. This isn't just a curiosity, it's a full-blown cosmic mystery that's forcing scientists to rethink the very fabric of reality. What makes this black hole so strange? Spin is supposed to be a fundamental feature of these cosmic monsters. When a massive star collapses, it doesn't just vanish, it leaves behind a swirling, spinning remnant, a gravitational whirlpool so powerful that not even light can escape. But this one, it's like a frozen top, perfectly still in a universe that never stops moving. The implications are staggering. If black holes don't have to spin, what else have we gotten wrong? Could there be other black holes out there, equally strange, hiding in the darkness? And most importantly, what does this mean for our understanding of gravity, space, and time itself? This isn't just a story about a weird black hole. It's a story about human curiosity, about the relentless drive to uncover the secrets of the cosmos. For decades, we've relied on Einstein's equations to map the universe, to predict how stars move, how galaxies collide, how time bends. But now, we're face to face with something that doesn't fit. And that's where things get exciting, because every time the universe throws us a curveball, it's an opportunity, a chance to learn something new, to push the boundaries of knowledge even further. So buckle up. We're about to dive into the heart of this cosmic anomaly, exploring the cutting-edge research, the wild theories, and the mind-blowing possibilities that come with a black hole that simply refuses to spin. By the end of this journey, you'll see why this isn't just a scientific oddity, it's a revolution in the making. To understand why this black hole is such an anomaly, we need to go back to the basics. Imagine a star massive, brilliant, burning fiercely for millions of years. When it runs out of fuel, it doesn't just fade away. It collapses inward with such force that it warps space and time itself, creating a black hole. Now here's the thing, most stars spin, and when they collapse, that spin doesn't just vanish. It gets concentrated like a figure skater pulling in their arms to spin faster. The result, a black hole that's whirling through space, dragging the very fabric of reality around it like a cosmic whirlpool. But this black hole, the one that refuses to spin, throws a wrench into that entire process. It's as if the universe hit the pause button. Normally, the spin of a black hole is a key part of its identity, influencing how it interacts with its surroundings, how it devours matter, even how it warps time nearby. Without spin, it's like a silent predator in the dark, behaving in ways we don't fully understand. Scientists have spent decades studying black holes, building models based on Einstein's theory of general relativity, and this discovery. It's making them question if they've missed something fundamental. Think of it like building a puzzle where all the pieces fit perfectly, until you find one that doesn't. It forces you to reconsider everything. Could there be another way black holes form, one that doesn't involve spinning stars? Are there invisible forces at play we haven't discovered yet? Or is this a hint that our understanding of gravity itself might need an update? The questions this discovery raises are as thrilling as they are daunting, because every time we think we've got the universe figured out, it throws us a curveball like this. And that's what makes science so exciting. It's not just about the answers we know, but the mysteries still waiting to be uncovered. Einstein's theory of general relativity is like the rulebook of the cosmos, a set of equations so precise they've predicted everything from bending starlight to the existence of gravitational waves. And when it comes to black holes, relativity paints a very specific picture. These cosmic beasts should spin. Why? Because the stars that form them are spinning. When a massive star collapses, its rotation doesn't just disappear. It gets compressed, amplified, turning the resulting black hole into a whirlpool of warped space-time. This isn't just a guess, it's baked into the math. The Kerr metric, a solution to Einstein's equations, describes spinning black holes so accurately that scientists use it like a blueprint. But here's the problem. Our rogue black hole doesn't follow the blueprint. It's like showing up to a dance where everyone's twirling except one person standing perfectly still. According to relativity, that shouldn't happen. The Kerr metric doesn't account for a black hole with zero spin, which leaves scientists scratching their heads. Did this black hole form without inheriting its star's rotation? Or is there something deeper, something we're missing about how matter behaves under such extreme conditions? One possibility is that this black hole didn't form the usual way. Maybe it wasn't born from a single collapsing star, but from something far stranger, like the merger of two black holes that cancelled out each other's spin. Picture two ice skaters spinning in opposite directions, colliding and coming to a complete stop. It's a rare scenario, but in the chaos of the universe, rare doesn't mean impossible. Then there's the even wilder idea. What if Einstein's equations, as brilliant as they are, aren't the full story? Could there be gaps in our understanding of gravity, hidden forces or effects that only show up in the most extreme environments? After all, relativity and quantum mechanics, the two pillars of modern physics, still don't play nicely together. This black hole might be a clue, a cosmic breadcrumb leading us toward a deeper theory, one that unifies the rules of the very large and the very small. For now, all we know is that this black hole is a rebel, a cosmic outlier refusing to follow the script, and that's exactly what makes it so thrilling. Every time the universe defies our expectations, it's not just a challenge, it's an invitation. An invitation to look deeper, think harder, and rewrite the rules if we have to. Because if there's one thing history has taught us, it's that the most interesting discoveries often come from the things that don't fit. The moment astronomers spotted this cosmic oddity, they knew something was profoundly wrong. It all started with faint echoes of X-rays flickering across the screens of the Chandra observatory, a telltale signature of matter spiraling into a black hole. But something about this signal stood out. Normally, as gas and dust plunge toward a black hole's event horizon, they don't just fall straight in. The black hole's spin whips them into a frenzied disk, heating the material until it glows fiercely in X-rays. The pattern of that glow, a skewed, lopsided shimmer, betrays the black hole's rotation, like fingerprints left at a crime scene. Yet this black hole's X-ray signature was eerily symmetrical. No Doppler shifts, no telltale distortions, just a calm, uniform glow, as if the material were falling straight into a cosmic pit with no swirl at all. At first, researchers wondered if their instruments were glitching, but as more telescopes from NASA, a new star to the European Space Agency's XMM Newton, turned their gaze toward the anomaly, the data only grew stranger. No matter how they crunched the numbers, the conclusion was inescapable. This black hole wasn't spinning, not even a little. The discovery sent shockwaves through astrophysics labs worldwide. Imagine poring over a textbook that's been gospel for decades, only to find a page that contradicts everything you've learned. That's what this felt like. Teams scrambled to double-check the data, running simulations, tweaking models, searching for any overlooked variable that could explain the impossible. Maybe the black hole's spin axis was pointed directly at us, hiding its rotation, or perhaps surrounding dust clouds were distorting the X-ray signals. But one by one, those explanations fell apart. The truth was staring them in the face. They'd found a cosmic renegade, a black hole that defied the most basic rules of its kind. What made this revelation even more unsettling was the sheer improbability of it all. Black holes should spin, just like planets, stars, and galaxies do. Even Earth's rotation comes from the ancient spin of the cloud that formed our solar system. For a black hole to have zero spin, it would have to form under freakishly precise conditions, like a star collapsing with perfect symmetry, its rotation somehow cancelled out at the moment of collapse. The odds of that happening naturally are astronomically low, yet here it was, and if one non-spinning black hole exists, how many others might be lurking in the shadows? Suddenly, astronomers found themselves questioning not just this object, but every assumption they'd ever made about how black holes are born. Could there be entire populations of these silent, motionless giants? Are they relics of some exotic process we haven't even imagined? Or is this black hole a cosmic fluke, a one in a trillion accident that's forcing us to rewrite the textbooks? One thing's certain, discoveries like this don't just add to our knowledge, they shatter the box we've built around it. And that's when science gets truly exciting. Because every time the universe hands us a mystery this profound, it's not just a gap in our understanding, it's a doorway. Spin isn't just a quirk of black holes, it's the engine that drives their most dramatic cosmic performances. Picture a whirlpool in space, so powerful it doesn't just swallow matter but twists the very fabric of reality around it. That's what happens when a black hole rotates. Space-time itself gets dragged along, like taffy stretched and wound into invisible spirals. This creates a zone just outside the event horizon called the ergosphere, where the rules of physics take a surreal turn. Here, nothing can stand still, not even light. The black hole's spin forces everything to move, and that motion unlocks something extraordinary: energy. In theory, we could harvest this energy like tapping into a cosmic power plant, but a black hole that doesn't spin, it's like a battery with no charge, a silent, static pit in space with no ergosphere, no twisted space-time, and no free energy up for grabs. Then there's the spectacle of relativistic jets, twin beams of superheated plasma screaming across the universe at nearly the speed of light. These jets are cosmic blowtorches, sculpting galaxies, sparking star formation, and even shutting down stellar nurseries with their sheer force. And guess what powers them? Spin. As matter spirals into a spinning black hole, magnetic fields get wound up like coiled springs, launching jets that can stretch for millions of light years. But a non-spinning black hole, it's eerily quiet. No jets, no fireworks, just a gravitational tomb that swallows everything without a whisper. That's the real puzzle here. If spin shapes how black holes interact with their surroundings, what happens when one doesn't play along? Galaxies might evolve differently. The energy balance of entire cosmic neighborhoods could shift. And that's not even the weirdest part. Black holes are supposed to be messy eaters, spinning as they gorge on gas and stars. So how did this one end up so still? Did it form in isolation, feasting on sparse material that never gave it a nudge? Or was it born from some exotic collision that cancelled out its rotation, like two spinning tops smashing together and stopping dead? The more we learn, the clearer it becomes. Spin isn't just a detail, it's a cornerstone of how black holes shape the universe. And when one breaks the mold, it doesn't just defy expectations. It forces us to ask what else we've missed in the dark. When the universe breaks its own rules, scientists don't just shrug, they dig deeper. And right now, they're racing to explain how a black hole could possibly refuse to spin. The leading theory, a cosmic collision so precise it erased rotation entirely. Picture two black holes, each spinning wildly, locked in a gravitational dance. As they spiral closer, their rotations could cancel each other out, like two whirlpools merging into a calm pond. When they finally collide, the resulting black hole might inherit no spin at all, a perfect zero. It's an incredibly rare scenario, but in a universe this vast, rare doesn't mean impossible. Then there's the even more exotic possibility. This black hole might be ancient, a relic from the universe's chaotic infancy. Primordial black holes, theorized to have formed in the first seconds after the Big Bang, could have emerged under conditions so extreme, the usual rules didn't apply. Unlike stellar black holes born from collapsing stars, these wouldn't inherit spin from a rotating parent. Instead, they'd be forged in the furnace of the early cosmos, where density fluctuations alone might have birthed them. If this black hole is primordial, it could be a time capsule carrying secrets from a time before stars even existed. But the wildest explanation of all, that we've stumbled upon a flaw in Einstein's equations. General relativity has been tested relentlessly for over a century, passing every trial with flying colors until now. Could this black hole be the first crack in the foundation, a hint that gravity behaves differently under the most extreme conditions? Some theorists whisper about quantum hair, hypothetical properties of black holes that might alter their spin dynamics in ways we can't yet model. Others wonder if dark energy or undiscovered particles play a hidden role. What's fascinating is how each theory, no matter how outlandish, forces us to expand our imagination. A merger that challenges our understanding of black hole dynamics, a primordial relic that opens a window to the universe's first moments, a breakdown in relativity. That could rewrite physics itself. One thing's clear, this isn't just about a single oddball black hole. It's about discovering whether the universe has more tricks up its sleeve than we ever dreamed. And that's why scientists aren't just puzzled, they're thrilled. Because when the cosmos throws you a curveball, it's not a dead end. It's an invitation to explore. Dark matter, the universe's most elusive ghost, might hold the key to this cosmic conundrum. We've long known it's out there, shaping galaxies with its invisible gravitational pull. But what if it's also shaping black holes in ways we never anticipated? Some researchers are now asking a radical question. Could dark matter be the reason this black hole refuses to spin? Think about how ordinary matter behaves. Stars, gas clouds, even planets, they all carry angular momentum, that inherent spin woven into the fabric of cosmic motion. When a star collapses, that spin doesn't vanish. It gets funneled into the newborn black hole, setting it whirling like a top. But dark matter, it's a different beast entirely. We've never directly observed it interacting with anything except through gravity. What if dark matter particles don't just lack charge or light? What if they lack spin itself? If a collapsing star were shrouded in a dense halo of such particles, could their motionless presence have somehow cancelled out the star's rotation, leaving behind a black hole frozen in stillness? This isn't just wild speculation. Simulations show that dark matter could pile up near black holes in surprising ways. Unlike normal matter, which heats up and radiates away energy as it falls inward, dark matter might linger in chaotic orbits, subtly altering the black hole's growth. In extreme cases, this could lead to a bizarre scenario: a black hole fed not by spinning gas disks, but by a slow, silent rain of dark matter particles that slip past the event horizon without so much as a whisper. The result, a black hole that grows without spinning, defying every expectation. But here's where it gets even stranger. If dark matter really did play a role, this black hole could be more than just an oddity. It might be a Rosetta Stone for decoding dark matter's true nature. Every other method of detecting it has hit walls. Underground labs, particle colliders, even space-based telescopes have come up empty-handed. But a non-spinning black hole. That could be a cosmic fingerprint, a clue written in gravity itself. By studying its behavior, we might finally glimpse how dark matter interacts with the most extreme objects in the universe. Of course, not everyone's convinced. Critics point out that dark matter's gravitational influence should be too diffuse to halt a black hole's spin entirely. Others argue that even if dark matter lacks angular momentum, it's hard to imagine it overpowering the violent chaos of a collapsing star. But that's the beauty of a mystery like this. It forces us to consider possibilities we'd never entertain otherwise. Maybe dark matter clumps in ways we haven't modeled. Maybe it interacts with black holes through some unknown force. Or maybe this black hole is showing us that dark matter isn't what we thought at all. One thing's certain, if dark matter is involved, the implications stretch far beyond a single rogue black hole. It would mean that this invisible scaffold of the cosmos doesn't just lurk in the shadows, it actively sculpts the most extreme objects in existence. And that realization could rewrite not just astrophysics, but our entire understanding of the universe's hidden architecture. Einstein's theory of relativity has been the bedrock of modern physics for over a century, but what if this stubborn black hole is a sign that the bedrock has cracks? When the universe serves up an anomaly this glaring, it's worth asking, could alternative theories of gravity finally get their moment in the spotlight? Take modified Newtonian dynamics, or MUND, for example. This controversial framework suggests that gravity doesn't behave the way Einstein predicted at all scales, especially in the faint outskirts of galaxies where stars whirl faster than they should. Proponents argue that MUND could explain cosmic oddities without invoking dark matter, and maybe, just maybe, it could account for a black hole that defies spin. Then there's loop quantum gravity, a radical approach that reimagines space-time itself as a woven fabric of tiny, discrete loops. Unlike string theory's extra dimensions, this framework keeps things grounded in 3 dimensions but suggests that space-time has a granular structure, like pixels on a cosmic screen. At the extreme densities near a black hole's core, these quantum grains might alter how gravity behaves, potentially allowing for scenarios where spin isn't inevitable. Imagine a black hole's heart not as a smooth warp in space-time, but as a knotted tangle of quantum threads where the usual rules of rotation fray at the edges. But the real wild card, emergent gravity, an idea that flips everything on its head, proposed by physicist Eric Verland. This theory suggests gravity isn't a fundamental force at all, it's a side effect of deeper, invisible interactions, like how temperature emerges from the motion of atoms. If gravity is more like thermodynamics than geometry, then black holes might not need to spin like cosmic whirlpools. They could be still, silent, and governed by entirely different mechanics. Of course, these theories aren't without their critics. MUND struggles to explain galaxy clusters without tweaks. Loop quantum gravity remains untested. And emergent gravity, it's so counterintuitive that many physicists still regard it as speculative. But here's the thing, science thrives on anomalies. Every time we hit a wall with established theories, that's when the most daring ideas get their chance to shine. This black hole might be more than a cosmic oddity. It could be the catalyst that pushes us toward the next great leap in physics. The beauty of this moment isn't just in the answers we might find, but in the questions we're forced to ask. If Einstein's equations need revising, where do we even begin? Do we tweak them at the edges or tear up the playbook entirely? And if alternative gravity theories can explain this black hole, what else might they reveal about the universe's hidden layers? One thing's certain, when a cosmic rebel like this shows up, it's not just breaking rules, it's rewriting them. And that's how revolutions start. Studying black holes is already like trying to eavesdrop on a whisper in a hurricane. But when one refuses to spin, it's like the whisper vanishes entirely. Normally, astronomers rely on two key clues to measure a black hole's rotation: the furious glow of its accretion disk and the telltale fingerprints in its X-ray emissions. Picture a whirlpool of superheated gas spiraling inward at nearly light speed, twisted by the black hole's spin into a lopsided, frenzied disk. That distortion creates an unmistakable signature, a Doppler effect that shifts light to higher energies on one side and lower on the other. It's like listening to a siren as it races past you, the pitch rising and falling, but with a non-spinning black hole, the disk stays eerily symmetrical. No Doppler shifts, no skewed light, just a uniform glow that gives away nothing. Then there's the X-ray paradox. Spinning black holes don't just swallow matter, they power some of the universe's most dazzling light shows. As gas plunges toward the event horizon, it tangles with magnetic fields wound tight by the black hole's rotation, launching jets of X-rays that flicker like cosmic Morse code. These flickers, called quasi-periodic oscillations, are the black hole's heartbeat, pulsing faster as the spin increases. But a static black hole, it's all silence. No magnetic springs to coil, no X-ray pulses to decode. Without spin, the black hole becomes a cosmic black box, swallowing everything without leaving a trace. This raises a chilling possibility. What if we've been missing an entire population of these silent giants? Most black holes we've detected are the loud ones, the spinning, feasting, X-ray bright beacons that scream their presence across the cosmos. But the ones that don't spin, they're cosmic ghosts, nearly invisible against the void. It's like searching for a jungle cat at night. By listening for its roar, you'll find the lions, but the silent stalking panthers. They could be everywhere and you'd never know. The challenge isn't just technical, it's philosophical. If nature can make black holes without spin, how many have slipped past our telescopes? And what does that mean for our census of the universe's darkest objects? Current estimates suggest there could be hundreds of millions of black holes in our galaxy alone. But if even a fraction lacks spin, our maps of the cosmos might be missing entire chapters. Worse, the tools we've built to hunt black holes might be biased toward the ones that spin. Take gravitational wave detectors like LIGO. They're exquisitely tuned to catch the ripples from colliding black holes, but those ripples are strongest when the black holes are rapidly rotating. A merger of two non-spinning black holes would send far fainter signals, easy to overlook in the noise. It's like tuning a radio to pick up rock music, but missing the classical station entirely. So how do we find these cosmic recluses? One hope lies in microlensing, watching for the subtle warping of starlight as an invisible black hole drifts in front of a distant star. Another is to hunt for the faintest X-ray whispers, the ones we've been filtering out as background noise. But even then, confirming a total lack of spin requires precision beyond most telescopes' limits. It's the ultimate cosmic hide and seek, where the hider doesn't just stay quiet, it erases the rules of the game. What's thrilling is that every observational hurdle is also an opportunity. If we can crack this puzzle, we might not just find more non-spinning black holes, we could uncover entirely new ways they form and evolve. After all, the universe loves to surprise us. And sometimes the biggest discoveries don't come from what's shining brightest, but from what's hiding in the shadows. For over a century, black holes have been neatly sorted into categories based on two simple traits: mass and spin. It's a cosmic filing system that's worked beautifully until now. The discovery of a black hole that refuses to spin doesn't just add a new specimen to the collection, it shakes the entire shelf. Suddenly, our tidy classifications feel incomplete, like trying to describe every animal on Earth using only size and color. What about the ones that don't fit? Take stellar mass black holes, for example. These are the remnants of collapsed stars, and astronomers have always assumed they inherit their parent star's rotation. That spin defines their behavior, how they feed, how they warp space-time, even how they merge with other black holes. But if some stellar mass black holes don't spin at all, they're not just outliers, they're a whole new subclass. Imagine discovering a species of bird that doesn't fly. You wouldn't just call it a strange bird. You'd need a new name, a new way to describe it. The same goes for these cosmic anomalies. Then there's supermassive black holes, the behemoths lurking at the hearts of galaxies. Their spin is thought to shape entire galaxies, influencing star formation and galactic evolution. But what if some of these giants are perfectly still? Current models suggest supermassive black holes grow by swallowing gas, stars, and even other black holes, a messy process that should leave them spinning like tops. A non-spinning supermassive black hole would imply a radically different growth history, one where matter fell in with near-perfect symmetry, like sand trickling straight through an hourglass. If such objects exist, they could rewrite the story of how galaxies form. The real challenge lies in detection. Right now, our tools are fine-tuned to find spinning black holes. Their accretion disks glow brightly, their jets scream across the cosmos, and their gravitational wave signals ring loud and clear, but a non-spinning black hole. It's the cosmic equivalent of a stealth bomber, nearly invisible unless it passes directly in front of a star. That means our current catalog of black holes might be skewed, missing entire populations of these silent objects. It's like conducting a wildlife survey by only counting animals that roar. This isn't just about adding a new column to a spreadsheet. Classification systems are the backbone of science. They shape how we ask questions, design experiments, and interpret data. If black holes don't need spin to exist, every textbook diagram, every simulation, every theory about their evolution needs a second look. Suddenly, the universe's darkest objects are showing us they're more diverse, more mysterious than we ever imagined. And that's the most exciting part of all, because when the rules change, science doesn't just adapt, it evolves. To crack the mystery of this spinless black hole, scientists are turning to some of the most powerful tools in modern astrophysics, supercomputers capable of recreating the cosmos itself. These aren't just fancy calculators, they're entire universes in silicon, running simulations so precise they can track the fate of a single atom spiraling toward a black hole's edge. The goal: to rewind time and test every possible scenario that could birth a black hole without spin. One simulation might start with a dying star collapsing under its own gravity, but with a twist. What if the star's rotation wasn't uniform? Imagine a sphere of gas with some regions swirling clockwise, others counterclockwise, like a celestial tug of war. As it collapses, those opposing spins could cancel each other out, leaving behind a black hole as still as a frozen pond. Another model might pit two black holes against each other, fine-tuning their collision until the merger's aftermath shows zero rotation. It's like watching cosmic billiards at the smallest scales, where the right impact could leave the final black hole perfectly motionless. But here's where things get even more intriguing. Some simulations are venturing beyond Einstein, testing modified gravity theories or exotic dark matter interactions. Picture a black hole forming in a cloud of invisible particles that sap its angular momentum, like a wheel grinding to a halt in thick syrup. Or a scenario where quantum effects at the tiniest scales alter how space-time warps, making spin optional rather than inevitable. These aren't just wild guesses, they're controlled experiments playing out in digital universes where physicists can tweak the laws of physics itself. The results so far, a mix of frustration and fascination. Some simulations do produce non-spinning black holes, but only under freakishly specific conditions, like a star collapsing with near-perfect symmetry or a merger fine-tuned to the nth degree. That raises a troubling question. If these scenarios are so rare, why are we seeing one now? Either we've hit a cosmic jackpot, stumbling upon a one-in-a-billion oddity, or our simulations are missing something fundamental. That's why the next generation of models is pushing further, incorporating factors we've long ignored. Maybe magnetic fields play a bigger role than we thought, stabilizing a collapsing star's rotation. Or perhaps black holes can shed spin through gravitational waves, like a spinning top losing energy to friction. Every new variable added to the simulation is another piece of the puzzle, another chance to glimpse the truth behind this cosmic rebel. What's thrilling is that even failed simulations teach us something. Every dead end rules out a possibility, narrowing the path toward an answer, and when the models finally align with reality, that's when the real magic happens, the moment we don't just solve a mystery, but uncover a deeper layer of the universe's design. Because if supercomputers can show us how a black hole breaks the rules, they might also reveal the new rules waiting to be written. Sometimes the answers to a cosmic mystery aren't hidden in the object itself, but in the neighborhood it calls home. To understand why this black hole refuses to spin, astronomers aren't just staring into the abyss, they're mapping the entire region around it, searching for clues etched into the fabric of its galaxy. Because black holes don't exist in isolation, they're shaped by their surroundings, by the gas they swallow, the stars they fling into chaos, even the dark matter halos that cloak their galaxies. So what does this black hole's environment tell us? First, there's the question of location. Is this rebel floating alone in the cosmic void, or is it nestled in a bustling galactic center? If it's isolated, that could hint at a violent past. Perhaps it was kicked out of a star cluster during a gravitational tussle, leaving it to wander silently through the darkness. But if it's surrounded by other objects, the patterns of nearby stars and gas clouds might reveal scars from ancient collisions or traces of a disrupted orbit. Imagine a crime scene where the dust hasn't settled yet. The way debris scatters can tell you exactly what went down. Then there's the matter of its last meal. Black holes are messy eaters, and the gas swirling around them usually bears the marks of their feeding frenzy. But this one's accretion disk, if it even has one, is eerily calm. That could mean it's been starved for eons, consuming material so slowly that its spin has ground to a halt. Or perhaps it devoured something unusual, like a slow, symmetric stream of gas that fell straight in without imparting any rotation, like water circling a drain with no swirl. The most tantalizing clues might come from the galaxy's overall structure. Galaxies with fast-spinning supermassive black holes often have tightly wound spiral arms or active jets carving through their cores. But a galaxy hosting a non-spinning black hole, it might look oddly undisturbed, like a pond with no ripples. Alternatively, if this black hole formed from a rare merger that cancelled out its spin, there could be gravitational echoes, subtle distortions in the orbits of nearby stars, like footprints frozen in time. Already, telescopes are scanning the region for these cosmic breadcrumbs. Spectrographs dissect the light from surrounding stars, hunting for telltale velocity shifts that betray the black hole's gravitational grip. Infrared cameras peer through dust clouds, mapping the distribution of gas for signs of past turbulence. Even the faintest anomalies, a star moving too fast, a gas cloud shaped too symmetrically, could rewrite the story of how this black hole came to be. What's becoming clear is that this isn't just about one oddball object. It's about the invisible threads connecting black holes to their galaxies, threads we're only beginning to tug on. Because if a black hole's spin really is tied to its environment, then finding more of these silent giants could reveal entirely new rules for how galaxies and their dark hearts evolve together. And that's a mystery worth unraveling, one clue at a time. Gravitational waves are the universe's way of ringing like a bell, ripples in space-time sent out when massive objects collide. When two black holes spiral toward each other and merge, they don't just vanish. They send shockwaves through the fabric of reality, vibrations so precise that detectors like LIGO and Virgo can pick them up millions of light years away. These waves carry fingerprints of the black hole's spins, their masses, even the angle of their collision. But here's the puzzle. If our spinless black hole was born from a merger, where's the gravitational wave signal? Think of it like a crime scene with no footprints. When black holes merge, the event should be anything but silent. The faster they spin, the stronger the gravitational waves, like a whirlpool churning up bigger waves the faster it rotates. But if two black holes collided in just the right way to cancel out their spins, the resulting waves would be faint, almost whisper quiet. It's possible LIGO and Virgo simply missed them, lost in the background noise of the cosmos. Or worse, what if the merger didn't produce waves at all? That would mean something fundamental is missing from our understanding of how space-time behaves during these cataclysmic events. There's another layer to this mystery. Gravitational wave detectors aren't just listening for any ripple. They're tuned to specific frequencies, like a radio scanning for familiar stations. Most mergers we've detected involve black holes with significant spin, creating waves that match our models. But a merger that produces a non-spinning black hole. That's off script. The waves might look completely different or be so subtle they slip through our nets entirely. It's like expecting a thunderclap and hearing only a sigh. This absence isn't just a technical hiccup, it's a clue. Maybe the black hole didn't form from a merger at all, but through some exotic process we haven't imagined. Or perhaps gravitational waves behave differently under extreme conditions, bending the rules in ways Einstein never predicted. Either way, the silence speaks volumes. Every time the universe refuses to follow the expected script, it's not just a gap in our knowledge. It's an invitation to listen more closely, to build better detectors, and to question what we think we know about the most violent events in the cosmos. The next generation of observatories, like the space-based LISA mission, might finally catch these elusive whispers. Until then, the missing signal remains a haunting reminder. The universe's deepest secrets often hide in what we don't hear, not just what we do. Magnetic fields are the invisible puppeteers of the cosmos, threads of force that can twist entire galaxies, shape stellar nurseries, and even dictate how black holes feast. So when scientists stumbled upon this spinless anomaly, one question burned brighter than the rest. Could magnetism be the culprit? Picture a black hole's birth, the moment a dying star collapses inward. Normally, the star's rotation gets funneled into the newborn black hole, setting it spinning like a top. But what if a powerful magnetic field intervened, acting like cosmic glue to slow or even halt that spin? Here's how it might work. As a star collapses, its magnetic fields don't just vanish, they intensify, winding tighter and tighter like coiled springs. In most cases, these fields align with the star's rotation, amplifying the spin as it collapses. but under rare conditions, the fields could become so strong they resist the star's motion, like dragging a spoon through honey. The result, a black hole that forms without the usual whirl, its birth rotation sapped by magnetic friction. Or consider the opposite scenario, a black hole born in a magnetic desert. Without the usual tangled fields to channel matter into a spinning disk, gas might plunge straight inward, like water vanishing down a drain with no swirl. No spin, no fireworks, just a silent gravitational pit. It's a radical idea, but not without precedent. Neutron stars, the dense leftovers of supernova, sometimes show bizarre behavior linked to their magnetic fields. A few even exhibit anti-glitches, sudden slowdowns that defy expectations. Could black holes have their own magnetic quirks we've yet to uncover? The challenge is proving it. Magnetic fields around black holes are fiendishly hard to measure. Unlike the blazing light of an accretion disk, magnetism leaves no direct glow, only subtle hints in the way it bends polarized light or shapes jets of plasma. Some researchers are now scouring data from radio telescopes, hunting for the telltale twist in light that betrays an ultra-strong field. Others are running simulations, testing how different magnetic configurations might freeze a black hole's spin over billions of years. But the implications stretch far beyond this one oddball. If magnetism can lock a black hole into stillness, it means these fields aren't just side players, they're architects, sculpting black holes in ways we never imagined. And that opens a chilling possibility. What if spin isn't the default? What if, under the right magnetic conditions, motionless black holes are more common than we thought? The universe has a way of reminding us that for every rule, there's an exception, and for every force we understand, there's another waiting to rewrite the script. As telescopes grow sharper and simulations more precise, we might finally glimpse the invisible hand guiding this cosmic rebel. Until then, the mystery lingers, a silent challenge to everything we thought we knew. Could this be the first time we've encountered a black hole that defies spin, or has the universe been quietly hiding others? The truth is, while vanishingly rare, whispers of similar anomalies have surfaced before. Back in 2012, astronomers studying a peculiar black hole in the galaxy NGC 1377 noticed something off. Its X-ray emissions lacked the telltale distortions of rotation. Then in 2019, another candidate emerged in the system H1743-322, where the data stubbornly refused to show any signs of spin. Neither case was conclusive, buried under layers of cosmic noise and competing explanations, but together they form a tantalizing pattern. What's striking is how these outliers cluster around similar environments, often in sparse galactic neighborhoods where star formation has slowed to a crawl. That's no coincidence. Without a steady influx of gas or nearby stars to feed on, a black hole's accretion disk could grow so faint that its spin becomes impossible to measure. But here's the twist. Some researchers argue these aren't measurement failures at all. They might be glimpses of an entirely different breed of black hole, one that formed under conditions so extreme, spin was never part of the equation. Take primordial black holes, hypothetical relics from the universe's first seconds. Unlike their stellar-born cousins, these wouldn't inherit spin from collapsing stars. They'd emerge from the raw chaos of the early cosmos, where density fluctuations alone could birth them. If even a handful survived to the present day, they'd look eerily like our spinless rebel, silent, dark, and utterly still. Then there's the merger scenario. When two black holes collide head-on with perfectly opposing spins, simulations show their rotation can cancel out, like waves crashing together and leaving behind a calm sea. But the most compelling clue might come from a completely unexpected corner: intermediate mass black holes. These elusive objects, heavier than star-sized black holes but lighter than supermassive giants, are thought to form through runaway collisions in dense star clusters. In 2020, a team studying the object M82X1 found hints it might lack spin, a shock, since such black holes should be spinning rapidly from countless mergers. If confirmed, it would suggest a formation process we've never imagined, one where growth doesn't automatically mean rotation. The lesson here isn't just that strange black holes exist, it's that they might be hiding in plain sight. Every time we dismiss an anomaly as noise or a measurement glitch, we could be missing a cosmic rebel staring back at us, and that's the real value of looking back at these historical maybes. They're not just footnotes, they're breadcrumbs leading us toward a deeper truth that the universe's rulebook has more exceptions than we ever dared to suspect. What if this spinless black hole isn't an anomaly at all but a fossil, a relic from the universe's violent birth? Some of the most daring theories in physics suggest that the Big Bang didn't just create stars and galaxies, it might have forged countless microscopic black holes, each no larger than an atom. These so-called primordial black holes could be lurking everywhere, invisible remnants of the cosmos's first chaotic moments. And here's the twist: unlike their stellar-born cousins, these ancient objects might not spin at all. Think about the conditions of the early universe, a seething, hyper-dense soup where quantum fluctuations could collapse into tiny knots of gravity in an instant. Without rotating stars to birth them, these black holes would form from pure density, like wrinkles frozen in the fabric of space-time. No spin, no accretion disks, just silent, minuscule gravity wells drifting through the cosmos for billions of years. If even a handful survived to the present day, they'd defy everything we know about how black holes behave. This isn't just wild speculation. Primordial black holes have long been candidates for dark matter, the invisible glue holding galaxies together. But while most theories assume these ancient objects would spin, recent calculations suggest otherwise. Quantum effects in the early universe might have prevented angular momentum from taking hold, leaving these black holes perfectly still. It's like rolling a ball down a hill, except the hill is so steep and jagged, the ball doesn't roll at all. The implications are staggering. If this spinless black hole is primordial, it could be the first direct evidence of a hidden population threading through the cosmos. Some might even be evaporating right now, their final moments releasing bursts of Hawking radiation too faint for our telescopes to catch. Others could be passing through Earth undetected, their tiny gravitational tugs mistaken for cosmic noise. But the real puzzle is how to find them. Primordial black holes don't scream their presence like their stellar counterparts. No glowing disks, no relativistic jets, just whispers of gravity bending light or subtly warping the paths of stars. New projects like the Vera Rubin Observatory are scanning the skies for these telltale distortions, while quantum sensors buried deep underground hunt for the faintest tremors of a microscopic black hole's passage. Of course, not everyone's convinced. Critics argue that if primordial black holes were common, we'd have spotted their effects by now. Yet every time we rule out one size range, another slips through the cracks. It's like trying to catch fog with a net. The harder you look, the more it seems to evade you. But that's what makes this theory so tantalizing. If even one spinless black hole turns out to be primordial, it wouldn't just solve a cosmic mystery, it would open a window to the universe's first second, a time before stars, before galaxies, before light itself. And that's the beauty of a rebel like this. It doesn't just break the rules, it forces us to ask whether the rules were ever complete to begin with. Whether it's a lone oddity or a hidden legion, one thing's clear: the universe still holds secrets older than time. The information paradox is one of the most baffling contradictions in modern physics. a cosmic tug of war between Einstein's relativity and quantum mechanics. At its heart lies a simple question: when matter falls into a black hole, what happens to the information it carries? According to quantum theory, information can never be destroyed. Yet relativity insists that whatever crosses a black hole's event horizon is lost forever, erased from the universe. For decades, this paradox has left physicists at an impasse. But now, this spinless black hole might be the key to cracking the puzzle wide open. Normally, a spinning black hole complicates things further. Its whirlpool, like gravity, twists space-time so violently that it scrambles any information falling in, like a cosmic shredder. But a black hole without spin, it's a simpler beast, a static pit where space-time isn't being dragged around it. That lack of rotation could mean information doesn't get mangled beyond recognition. Instead, it might linger near the event horizon in ways we can finally detect. Picture throwing a book into a tornado versus dropping it into a still pond. One scatters the pages beyond recovery, the other leaves ripples we might still read. Some theorists suggest this could revive Stephen Hawking's old idea of soft hair, tiny, barely detectable imprints left on a black hole's horizon that encode information about what fell in. Without spin muddying the waters, these quantum fingerprints might be clearer, like footprints preserved in fresh snow rather than blown away by wind. Others speculate that a non-spinning black hole's calm exterior could make Hawking radiation, the faint glow of particles escaping black holes, more uniform, carrying away information in a steadier, decipherable stream. Then there's the holographic principle, the mind-bending idea that all the information inside a black hole might be encoded on its two-dimensional surface. For spinning black holes, this hologram gets warped and distorted, but a static one, its surface could act like a pristine hard drive, storing data in neat, orderly patterns. If true, this rebel black hole might be the Rosetta Stone that finally lets us decode how information survives the universe's most destructive forces. Of course, not all roads lead to answers. Some argue that spin has little to do with the paradox, that information escapes in ways we haven't imagined, regardless of rotation. Others warn that even a still black hole's quantum chaos might be too complex to untangle. But that's the thrill of a mystery like this. Every anomaly forces us to rethink the problem from new angles, to test theories we'd once dismissed. Whether this black hole solves the paradox or deepens it, one thing's certain: the universe loves a good plot twist, and this time the twist might rewrite the rules of reality itself. The moment news of the spinless black hole broke, it set off a chain reaction across the scientific community and beyond. Headlines screamed about the rebel black hole and Einstein's nightmare, while social media lit up with memes comparing it to everything from a broken record to a cosmic glitch in the Matrix. But beneath the buzz, there was a palpable sense of awe. For the first time in decades, physicists found themselves staring at something that didn't just challenge a minor theory, it shook the foundations of how we understand gravity itself. At conferences from Tokyo to Berlin, researchers who'd spent their careers debating the finer points of black hole mechanics suddenly had a new puzzle to untangle. Panel discussions turned into lively sparring matches, with theorists tossing out wild ideas and observational astronomers scrambling to double-check their data. The RZIV preprint server, where scientists share cutting-edge research before formal publication, saw a flood of papers overnight, some proposing elegant solutions, others tearing apart long-held assumptions. One team suggested dark matter interactions could explain the missing spin, while another argued for an entirely new class of black holes born from quantum fluctuations in the early universe. The debates weren't just academic, they were electric, the kind of fervor that only comes when the rules of the game might be changing. Meanwhile, the public's imagination ran wild. Podcasts dissected the discovery for casual listeners, YouTube explainers racked up millions of views, and even late-night talk shows cracked jokes about the universe's latest plot twist. What made this black hole so relatable was its sheer defiance. It wasn't just another distant cosmic oddity. It felt personal, like the universe itself had decided to poke holes in the textbooks. Teachers used it to spark classroom debates, artists turned it into surreal digital paintings, and sci-fi writers hastily rewrote drafts to include this newfound cosmic rebel. But the real surprise came from the collaboration it inspired. Astronomers who usually competed for telescope time began pooling resources, sharing data across continents to pin down the black hole's properties. Citizen scientists sifted through old star surveys, hunting for overlooked clues. Even tech companies offered up AI tools to help model scenarios faster. The discovery didn't just raise questions, it forged connections, proving that the most thrilling mysteries are the ones that remind us how much we still have to learn. And that's the heart of it all. Whether you're a physicist reworking equations at a whiteboard or a teenager staring at the night sky, this black hole does something rare. It makes the universe feel alive, unpredictable, and far stranger than we ever imagined. The excitement isn't just about solving a puzzle, it's about realizing there are still puzzles left to solve. The discovery of a black hole that defies spin hasn't just puzzled scientists, it's sparked a race to unlock its secrets with the next generation of cosmic observatories. At the forefront is the James Webb Space Telescope, a technological marvel designed to peer deeper into the infrared universe than ever before. While Webb can't see the black hole directly, its unmatched sensitivity could reveal the subtle fingerprints of this anomaly in the surrounding gas and stars. Imagine studying a crime scene not by the bullet holes, but by the way dust has settled in the aftermath. Webb might catch the faint infrared glow of material falling into the black hole at odd angles, or spot distortions in nearby star clusters that hint at its unusual gravitational pull. Every observation could be a clue, helping astronomers piece together whether this object is a cosmic fluke or the first of many. Then there's LISA, the Laser Interferometer Space Antenna, set to launch in the next decade. Unlike ground-based detectors like LIGO, LISA will float in space, free from Earth's vibrations, with laser arms stretching millions of kilometers. This makes it exquisitely sensitive to low-frequency gravitational waves, the kind that might ripple out if this spinless black hole ever merges with another. Picture dropping a pebble into a still pond versus a choppy ocean. LISA could detect the faintest ripples from collisions that other observatories would miss. If this black hole was born from a rare merger, LISA might catch similar events in action, revealing whether these cosmic rebels form in silence or with a gravitational whisper. But the real game-changer could be the Vera Rubin Observatory, with its gargantuan camera scanning the entire southern sky every few nights. While most telescopes focus on one target at a time, Rubin will catch fleeting changes like a star briefly flickering as an invisible black hole passes in front of it. If more spinless black holes exist, Rubin's relentless gaze might finally spot them hidden in plain sight. It's like turning on a flashlight in a dark room and realizing the walls were covered in writing all along. What astronomers hope to learn goes far beyond this one anomaly. Webb could uncover whether these black holes alter their galaxies differently, their stillness leaving a unique mark on star formation. LISA might reveal if their mergers emit gravitational waves in unexpected patterns, rewriting our models of space-time itself. And Rubin could answer the most haunting question of all. Is this black hole a loner, or part of a hidden population that's been lurking undetected for billions of years. Every new mission is a window into the unknown, a chance to test whether our cosmic rulebook needs a revision or a full rewrite. And with each observation, we're not just solving a puzzle. We're learning how to listen to the universe's quietest rebels, the ones that don't play by the rules. Science has always operated under the assumption that the universe plays by consistent rules, laws so fundamental they apply everywhere, from the atoms in our bodies to the farthest reaches of space. Einstein's theory of relativity is one of those bedrock principles, a framework so reliable it's predicted everything from Mercury's orbit to the bending of starlight. But now, this spinless black hole throws a wrench into that certainty. If a cosmic object can defy one of relativity's core predictions, what does that mean for our trust in scientific laws? Are they truly universal, or are they just approximations, guidelines that hold until we stumble upon the exceptions that prove them incomplete? This isn't just about black holes. It's about how we understand the very nature of discovery. For centuries, science has progressed by uncovering patterns, formulating rules, and then refining them when new data doesn't fit. Think of Newton's laws of motion, brilliant for their time, yet eventually superseded by Einstein's relativity when Mercury's orbit didn't behave as predicted. Each time we hit a wall, it's not a failure, it's an invitation to dig deeper. The spinless black hole might be our modern Mercury moment, a cosmic nudge telling us there's more to gravity than we've accounted for. But here's the twist: exceptions don't weaken science, they strengthen it. When we find phenomena that don't fit, it forces us to ask better questions. Maybe the laws aren't broken at all. Maybe they're part of a larger, more nuanced framework we haven't grasped yet. Quantum mechanics and relativity already operate in uneasy truths, each reigning supreme in their own domains. Could this black hole be a bridge between them? A clue that the true laws of the universe are stranger and more flexible than we've dared to imagine. Philosophers of science have long debated whether laws are discovered or invented, whether we're uncovering eternal truths or constructing models that merely approximate reality. This black hole leans into that debate. If nature can produce objects that sidestep our most cherished theories, it suggests the universe isn't bound by human logic. The rules we've written might be less like commandments and more like translations, imperfect attempts to decode a cosmos that's always one step ahead. That's the real gift of this cosmic rebel. It doesn't just challenge Einstein, it challenges our entire approach to knowledge. Because the most profound breakthroughs don't come from confirming what we already know. They come from the moments when the universe looks us in the eye and whispers, "Think again." Astronomers have turned the cosmos into a detective story, hunting for more of these silent, spinless black holes that defy expectations. The discovery of even one was shocking enough. But if they find others, it could rewrite our cosmic rulebook entirely. Teams across the globe are now sifting through decades of telescope data, re-examining old observations with fresh eyes, searching for the faintest hints of similar anomalies. It's like realizing you've been missing an entire species of animal in a forest you thought you knew by heart. The search isn't just about confirming a hunch, it's about patterns. One rogue black hole could be a cosmic accident, a statistical outlier in a universe teeming with chaos. But 2, 3, that's a trend. That's evidence of a hidden population, a class of objects we've overlooked because our tools and theories weren't looking for them. Imagine thinking all birds could sing, only to stumble upon a silent species no one had ever noticed before. Suddenly, the forest sounds entirely different. The challenge lies in the hunt itself. Non-spinning black holes are masters of camouflage. Without the telltale distortions of a whirling accretion disk or the energetic jets powered by rotation, they don't announce their presence like their spinning siblings. Astronomers have to get creative, combing through indirect clues, like the way these black holes warp the light of stars behind them or the subtle tug they exert on nearby gas clouds. It's detective work on a galactic scale, piecing together a case from circumstantial evidence. Some researchers are focusing on quiet corners of the universe, regions where black holes might have gone hungry for eons, their spin gradually winding down like a forgotten top. Others are zeroing in on dense star clusters where chaotic collisions could have birthed these oddities. And then there are the mavericks, digging through archival data from retired telescopes, hoping to spot overlooked anomalies buried in old observations. Every potential candidate gets scrutinized, debated, and tested because in science, one aha moment needs a chorus of confirmation to become a breakthrough. What's electrifying is how much this search could reveal, even if it comes up empty. If no other spinless black holes are found, it might mean this one truly is a cosmic unicorn, formed under freakishly rare conditions. But if they're out there, hiding in plain sight, that's a paradigm shift waiting to happen. It would mean our universe has been quietly assembling black holes in ways we never imagined, under rules we're only beginning to glimpse. And that's the thrill of the hunt, not just what we find, but what the search itself teaches us about the cosmos's endless capacity to surprise. Supermassive black holes have always played by their own rules, cosmic behemoths spinning at dizzying speeds, their gravity shaping entire galaxies. But could their smaller stellar mass cousins, like our spinless rebel, operate on an entirely different playbook? It's a question that forces us to rethink everything we thought we knew about how black holes evolve. At the heart of most galaxies, including our own Milky Way, sits a supermassive black hole, and nearly every one we've observed spins furiously, some approaching the speed of light. Their rotation isn't just a quirk, it's a defining feature, powering jets of energy that can outshine entire galaxies and sculpting the stars around them into swirling orbits. Yet here's the twist: while supermassive black holes seem to follow a predictable script, their smaller stellar mass counterparts might be far more unpredictable. The spinless anomaly we've discovered suggests that the rules governing these two classes of black holes could diverge in ways we never anticipated. For supermassive giants, rapid spin seems inevitable. They grow by devouring gas, stars, and even other black holes over billions of years, each merger and meal adding to their whirl. But stellar mass black holes, their lives are far more chaotic, shaped by violent stellar explosions, asymmetric collapses, and chance encounters in crowded star clusters. Maybe, just maybe, they don't always inherit the same relentless spin. Consider how they form. A supermassive black hole feasts continuously, its spin fed by a near-constant buffet of matter swirling into its maw. But a stellar mass black hole might go hungry for eons, its accretion disk fading to near nothingness, its spin gradually winding down like a forgotten top. Or perhaps it forms from a star that somehow collapsed without imparting rotation, a freakishly symmetrical implosion like a perfectly deflating balloon. The more we study these smaller black holes, the clearer it becomes. They might not be scaled-down versions of their supermassive siblings. They could be an entirely different beast. This isn't just an academic distinction, it's a clue to how black holes shape the universe at every scale. Supermassive black holes dictate the fate of galaxies, their spin influencing star formation and galactic structure. But stellar mass black holes, their role is more subtle yet no less critical. They litter the cosmos, drifting through space, occasionally flaring to life when they snag a passing star or gas cloud. If some of them lack spin, their behavior could be radically different. less likely to launch jets, less efficient at converting matter into energy, even less visible to our telescopes. The real mystery is whether these spinless outliers are rare accidents or part of a hidden population we've overlooked. If supermassive black holes are the roaring rivers of the cosmic landscape, could stellar mass ones include still, silent ponds we've never noticed? The answer might rewrite not just our understanding of black holes, but the invisible threads connecting them across the universe's vast tapestry. Black holes aren't just gravitational monsters, they're cosmic ovens, radiating heat and possessing entropy like any other thermodynamic system. But here's the twist: spin plays a starring role in that heat exchange. A rotating black hole acts like a frenetic dynamo, stirring space-time around it and generating energy that can be extracted through mechanisms like the Penrose process. Strip away that spin, and the entire thermodynamic script flips. A non-spinning black hole isn't just still, it's a fundamentally different kind of furnace, one that radiates heat without the whirl of relativistic drag. Take temperature first. For a spinning black hole, the faster it rotates, the cooler its event horizon becomes. The energy tied up in its spin actually lowers the surface temperature, like an ice skater slowing their spin to warm up. But a static black hole, its temperature depends solely on mass. The smaller it is, the hotter it burns. Without spin to redistribute energy, all the heat concentrates at the horizon, making it a far more intense thermal emitter. Picture a campfire versus a blast furnace. Both radiate heat, but one does it with quiet efficiency, the other with raw, unfiltered power. Then there's entropy, the measure of disorder within a system. For a spinning black hole, entropy intertwines with rotation, spreading across the ergosphere like ink swirling in water. But a non-spinning black hole's entropy is simpler, yet no less profound. It scales precisely with the area of its event horizon, a clean one-to-one relationship that hints at something deeper. Some theorists argue this simplicity might be a clue, a sign that static black holes obey thermodynamics in its purest form, uncomplicated by rotational chaos. What's truly fascinating is how these differences ripple outward. A spinning black hole can power quasars and light up galactic cores with its rotational energy. But a non-spinning one, its energy output is quieter, more thermal, like the steady glow of coals rather than the flare of a jet engine. That could mean galaxies anchored by these silent giants evolved differently, their central engines lacking the spin-driven fireworks that trigger star formation or quench it. Theorists are now racing to model these thermodynamic quirks, running equations that twist space-time without rotation to see what emerges. Early results suggest static black holes might be ideal laboratories for testing Hawking radiation, their lack of spin offering a cleaner signal of quantum effects at the horizon. Others wonder if their entropy holds secrets about quantum gravity, a Rosetta Stone for decoding how information escapes a black hole's grip. But the most tantalizing question remains: if spin alters a black hole's thermodynamics so drastically, what else have we overlooked? Could there be entire classes of cosmic objects radiating heat in ways we've never imagined? The universe, it seems, has more than one way to burn. Roger Penrose's cosmic censorship hypothesis is like the universe's ultimate spoiler shield, a rule that says singularities, those infinitely dense points at the heart of black holes, must always be veiled behind event horizons. No naked singularities allowed. It's nature's way of keeping its most chaotic secrets hidden, ensuring the fabric of reality doesn't unravel in unpredictable ways. But now, with this spinless black hole staring us down, we have to ask, does its bizarre behavior poke holes in Penrose's elegant idea? At first glance, the hypothesis seems safe. Even a non-spinning black hole still has an event horizon, that point of no return where gravity's grip becomes inescapable. but dig deeper and things get murky. The cosmic censorship conjecture isn't just about horizons existing, it's about stability. Spinning black holes with their ergospheres and twisted space-time are messy beasts, but their chaos is contained. A static black hole, though, it's simpler, yes, but that simplicity might come with its own risks. Without rotation's balancing act, the singularity at its core could, in theory, become more exposed to the outside universe under certain extreme conditions. Think of it like a storm. A spinning black hole is a hurricane, its fury organized into a predictable structure, but a non-spinning one, it's more like a sudden vacuum collapse, unpredictable, with no rotational force to stabilize it. Some theorists worry that under rare circumstances, like a near-perfectly symmetrical collapse or a collision that strips away angular momentum entirely, the event horizon might fracture, even briefly, offering a peek at the singularity beneath. And that's where cosmic censorship could falter. Penrose himself imagined singularities as cosmic taboos, forbidden from naked exposure because their infinite densities would break physics as we know it. Yet if this black hole formed through a freak merger or some exotic quantum process, could it skirt the rules? The math gets dicey here. Simulations of head-on black hole collisions sometimes show fleeting moments where horizons stretch thin, like a soap bubble about to pop. While no one's claiming this spinless rebel is currently flaunting a naked singularity, its existence hints that the universe's censorship board might have loopholes. The real test lies in the extremes. If we could find a black hole with just slightly less spin, or one born from conditions even more peculiar, would the hypothesis hold? Or would we be staring into the abyss literally? For now, the cosmic censor's job seems secure, but this black hole has opened a door to questions we're only beginning to explore. And behind that door might lie not just answers about singularities, but about whether the universe's rules are as ironclad as we thought. What if this spinless black hole isn't just breaking our universe's rules, it's following someone else's? The multiverse theory, long the playground of physicists and sci-fi writers alike, suggests our cosmos might be one of countless others, each with its own unique laws of physics. In some of those universes, gravity could behave differently, stars might collapse without spinning, and black holes could form as perfectly still voids. Could this anomaly be a cosmic interloper, a fingerprint from a parallel reality where the rules we take for granted simply don't apply? It sounds like the stuff of fantasy, but the math isn't as far-fetched as you'd think. In certain brain cosmology models, theories where our universe exists as a membrane floating in higher dimensional space, black holes could act as bridges between worlds. These black hole portals might not just connect distant points in our universe, they could thread the needle between entirely separate realities. If that's true, then a black hole that refuses to spin might not be a glitch in our system. It could be a relic, a scar left behind by a collision with another universe's physics. Think of it like finding a snowflake in the desert. In our universe, black holes spin because the stars that birth them spin. It's as fundamental as snow requiring cold. But if that snowflake drifted in from a place where snow falls in the heat, its very existence hints at a world beyond our own. Similarly, this black hole's stillness might be a clue that somewhere in a reality with different constants or forces, objects like this are the norm. Of course, not everyone's convinced. Critics argue that invoking the multiverse is a cop-out, a way to explain away mysteries without real evidence, and they're right to be skeptical. Extraordinary claims require extraordinary proof, and so far, no one's detected concrete signs of parallel universes. But here's the thing, science often advances by chasing the seemingly impossible. Quantum mechanics was once dismissed as absurd. Black holes themselves were considered mathematical curiosities until we found them. The multiverse might sound like wild speculation today, but tomorrow, it could be the key to unlocking this black hole's secret and rewriting our place in the cosmos. The beauty of this idea isn't just in its audacity, it's in how it reframes the mystery. If this black hole is a visitor from another reality, it's not an outlier, it's a messenger, and its message could be the most thrilling of all, that the universe or universes are far stranger and more wonderful than we ever dreamed. There's a quiet humbling in realizing that for all our telescopes, equations, and supercomputers, the universe still holds mysteries that defy our best theories. This spinless black hole isn't just a scientific oddity, it's a cosmic reminder that human knowledge has edges, boundaries we haven't even glimpsed yet. Think about it, we've mapped the human genome, split the atom, and sent probes beyond our solar system. Yet here we stand, staring at an object that shouldn't exist, whispering questions we don't yet have the tools to answer. This moment crystallizes something profound about the nature of discovery. Science isn't a ladder we climb toward some final, absolute truth. It's more like wandering through an endless forest, where every clearing reveals new horizons and new shadows. A century ago, Einstein's relativity felt like the final word on gravity. Now, this black hole hints that the story might have chapters we haven't even imagined. It's not that our theories are wrong, they're incomplete, like trying to describe an ocean by studying only its waves. What's striking is how these gaps in understanding aren't failures, they're invitations. Every time the universe throws us a curveball, it's not to mock our ignorance but to nudge us toward deeper questions. When Newton's laws couldn't explain Mercury's orbit, it led to relativity. When quantum particles defied logic, it birthed entirely new fields of physics. This black hole, it might be the catalyst for the next great leap, the anomaly that forces us to see gravity, space, and time in a new light. But there's a deeper lesson here, one that transcends equations. In a world where we're conditioned to expect instant answers, this cosmic rebel teaches patience. Some puzzles take generations to solve, some require tools we haven't invented yet, and that's okay. The beauty of science lies not just in the answers we find, but in the questions we learn to ask. This black hole isn't just challenging Einstein, it's challenging us to stay curious, to embrace uncertainty, to remember that the universe owes us nothing, and every revelation is a gift. Perhaps that's the most thrilling part of all. We're not at the end of discovery, we're somewhere in the messy, exhilarating middle. And if a single black hole can upend our expectations, imagine what else is out there, waiting in the dark. The hunt for cosmic oddities like our spinless black hole isn't just for professional astronomers anymore. It's a mission that's spilling over into the hands of everyday stargazers and data detectives. Across the globe, amateur astronomers are training their backyard telescopes toward the void, while online volunteers sift through mountains of telescope data, searching for the faintest hints of other anomalies hiding in plain sight. This isn't just science by committee, it's a revolution in how discoveries are made. When the universe throws us a curveball, sometimes the best way to catch it is to cast the widest net possible. Take the Zooniverse platform, where hundreds of thousands of volunteers, teachers, students, retirees, even kids analyze real astronomical data in their spare time. Projects like Black Hole Hunters task participants with scanning X-ray signals for patterns that might betray the presence of hidden black holes, including those that defy expectations. It's like a cosmic version of Where's Waldo, except the stakes are infinitely higher. In 2021, a retired computer scientist in Portugal spotted irregularities in a dataset that professional algorithms had missed, leading researchers to a previously overlooked black hole candidate. Could the next spinless rebel be uncovered by someone scrolling through data on their lunch break? The answer might surprise you. Then there's the rise of citizen supercomputers. Platforms like Einstein at home harness idle processing power from volunteers' laptops and phones, crunching gravitational wave data in the background. This distributed computing approach has already helped identify dozens of neutron stars, and now it's being retooled to search for the quietest black holes, the ones that slip past traditional detection methods. Imagine your phone while charging overnight, helping to pinpoint a black hole that upends Einstein's rules. That's the power of collective curiosity. But the real game changer might be the flood of data from next-gen telescopes like the Vera Rubin Observatory, which will generate more images in a single night than most telescopes produce in a year. No team of professionals, no matter how large, could hope to process that deluge alone. That's where the crowd comes in, by training amateur sleuths to flag anomalies, whether it's a star that flickers oddly or a patch of sky that's suspiciously dark. We're effectively turning the entire planet into a search party for the universe's weirdest outliers. What's thrilling is how these efforts are rewriting the script of discovery. Science has long been seen as the domain of elites in ivory towers, but projects like these prove that breakthroughs can come from anywhere. A high school student in Mumbai might notice a data glitch that turns out to be a cosmic revelation. A farmer in Iowa with a passion for astrophotography could capture the flicker of a dying star that hints at a hidden black hole. When it comes to unraveling the universe's mysteries, sometimes the most valuable tool isn't a billion-dollar telescope. It's the collective curiosity of millions of eyes, all looking up and asking, what if? This isn't just about finding more black holes. It's about redefining who gets to participate in the grand adventure of science. Every time an amateur spots something strange or a volunteer flags an anomaly, they're not just aiding professionals, they're becoming explorers themselves, pushing the boundaries of knowledge alongside the experts. And in a field as vast and enigmatic as astrophysics, that kind of collaboration isn't just helpful, it's essential, because the universe doesn't care who solves its puzzles, only that someone keeps trying. Mathematics has always been the silent partner to astrophysics, the unseen scaffolding holding up our understanding of the cosmos. From Newton's calculus to Einstein's tensor equations, every leap in our cosmic comprehension has been fueled by breakthroughs in math. But now, faced with a black hole that defies spin, we're forced to ask, have we hit the limits of our current mathematical toolkit? The equations that flawlessly describe spinning black holes, the Kerr metric, the Penrose diagrams, the intricate dance of differential geometry all crumble when applied to this motionless enigma. It's like trying to unlock a door with the wrong key. No matter how elegantly crafted, the tool just doesn't fit. The heart of the problem lies in symmetry, or rather, the lack of it. Spinning black holes are messy, dynamic systems, their asymmetries neatly accounted for in Einstein's field equations, but a perfectly static black hole. It's so symmetrical, so unnervingly simple, that the math we've relied on for decades suddenly feels over-engineered. Imagine building a supercomputer to solve a problem that only requires an abacus. The complexity of our existing frameworks might actually obscure the truth, burying the answer under layers of assumptions that no longer apply. Some theorists argue we don't need more complex math, we need math that's radically simpler, stripped back to its bare essentials to reveal what's been hiding in plain sight. This isn't just about tweaking a few variables. The challenge runs deeper, touching on one of the most tantalizing unsolved problems in physics, the the marriage of quantum mechanics and general relativity. Black holes sit at the intersection of these two worlds, and while relativity handles their gravity, quantum theory should govern their microscopic behavior. Yet without spin, that crucial bridge between the large and the small, the equations refuse to reconcile. It's as if the universe handed us a jigsaw puzzle where the pieces from different boxes don't just fail to connect, they're not even the same shape. Enter the mathematicians armed with fresh ideas that sound like science fiction. Non-commutative geometry, for instance, reimagines space-time as a web of relationships where coordinates don't follow the usual rules of algebra. In this framework, a black hole's event horizon might not be a sharp boundary but a fuzzy, probabilistic zone, a concept that could explain why spin isn't mandatory. Then there's holographic duality, the mind-bending notion that our three-dimensional universe might be a projection of information encoded on a two-dimensional surface. If true, a non-spinning black hole could be a flaw in the projection, a glitch in the cosmic code where the math of lower dimensions doesn't translate cleanly to higher ones. But the most provocative possibility, that we've been missing a mathematical language altogether. History shows us that revolutionary physics often demands new notation. Newton invented calculus to describe gravity. Einstein borrowed tensors from obscure geometry to formulate relativity. Could this black hole be pointing toward an undiscovered branch of math, one that doesn't yet exist in our textbooks? Some researchers are already sketching the outlines of such a framework, tentatively dubbed topological gravity, where the shape of space-time matters more than its motion. It's a long shot, but so was quantum mechanics a century ago. The beauty of this challenge is that it's not just about solving a single cosmic riddle. It's about expanding the very language we use to describe reality. Every time the universe throws us a curveball, from Mercury's orbit to quantum entanglement, we've responded not by giving up, but by inventing new ways to think. This black hole might be the catalyst for the next great mathematical revolution, one that doesn't just explain why it refuses to spin, but reshapes how we see the fabric of the cosmos itself. And that's the thrill of the unknown. The equations we're missing today could be the ones that unlock tomorrow's universe. Black holes aren't eternal. Even these cosmic titans fade away, slowly evaporating through a process called Hawking radiation. But here's where spin throws a wrench into the cosmic clockwork. A spinning black hole isn't just a gravitational vortex. It's a master of energy conservation, using its rotation to stave off decay like a whirlpool resisting the pull of the drain. The faster it spins, the more efficiently it traps particles near its event horizon, slowing the rate at which it leaks energy into the void. It's the universe's ultimate battery, stretching its lifespan by tapping into its own motion. But what happens when the battery is dead, when a black hole, like our spinless rebel, has no rotation to draw from? Does it wither faster, or does it cling to existence in ways we haven't predicted? Hawking radiation itself is a quantum quirk, born from particle-antiparticle pairs flickering in and out of existence at the edge of a black hole's gravity. Normally, one particle falls in while the other escapes, carrying away a tiny bit of the black hole's mass. But spin changes the game. A rotating black hole's ergosphere, that warped region of space-time dragged around it, supercharges this process, creating more opportunities for particles to escape. The result, a spinning black hole leaks energy slower, like a faucet with a tight valve. Remove the spin and the faucet widens. Theoretical models suggest a non-spinning black hole should radiate energy faster, shrinking more quickly toward its inevitable demise. Yet this rebel black hole might have other ideas. Without the chaotic turbulence of rotation, its event horizon could be calmer, more orderly, a smooth surface where quantum effects play out differently. Some calculations hint that without spin's distortions, Hawking radiation might emerge in a purer, more constant stream, like steam rising evenly from a still pot rather than sputtering from a boiling one. That could mean a shorter lifespan, yes, but it might also mean a more predictable decay, offering scientists a cleaner laboratory to study how black holes evaporate. Then there's the wild card. What if Hawking radiation isn't the whole story? Spin isn't just about energy conservation. It's about how a black hole interacts with the quantum foam of space itself. Without rotation, the microscopic structure of the event horizon might behave differently, perhaps even suppressing radiation in ways we haven't modeled. Imagine a spinning black hole as a stormy sea, churning up particles while a static one is a frozen lake, its surface too still to splash. Could the absence of spin create conditions where evaporation stalls or even reverses under rare circumstances? The stakes here aren't just academic. If spin dramatically alters a black hole's lifespan, it means the cosmos could be littered with ancient, non-spinning relics black holes that outlasted their whirling siblings by eons. Or conversely, it might mean the universe has already erased most of its spinless black holes, leaving behind only the rare stragglers like the one we've found. Either way, this isn't just about one oddball object. It's about rewriting the timeline of black holes themselves, and in doing so, uncovering new rules for how the universe handles its most enigmatic creations. What's thrilling is that we might not have to wait millennia for answers. Next-generation gravitational wave detectors could catch the faint death rattles of evaporating black holes, their final bursts of radiation carrying clues about how spin or its absence shapes their final moments. Until then, this cosmic rebel stands as a reminder. Even in death, black holes refuse to follow the script, and that's how we know we're onto something big. The very idea of manipulating black holes feels like science fiction, like reaching into the cosmos with godlike hands to tweak the universe's most destructive forces. But with theoretical advances in astrophysics and hypothetical technologies like gravitational wave manipulation or quantum engineering, the question shifts from can we to should we. Imagine a future where we could nudge a black hole's spin, siphon its energy, or even in the wildest scenarios harness it as a power source or cosmic propulsion system. The ethical dilemmas this raises are staggering. Who gets to decide whether humanity should tamper with an object that shapes galaxies? What happens if we accidentally destabilize a black hole's delicate balance, triggering unforeseen consequences for nearby star systems? This isn't just about capability, it's about responsibility. Consider the parallels to climate engineering here on Earth. We've seen how tampering with one part of a complex system, like injecting aerosols into the atmosphere to cool the planet, can have cascading, unpredictable effects. Now scale that up to a cosmic level. A black hole isn't an isolated lab experiment. It's a gravitational anchor, often surrounded by orbiting stars, nebulae, and even habitable planets. Tweaking its properties could alter orbits, disrupt stellar nurseries, or redirect deadly radiation jets. The stakes aren't just academic, they're existential. Would we, as a species, have the right to risk entire civilizations light years away for our own benefit? Then there's the philosophical angle. Black holes have existed for billions of years, long before life emerged on Earth. They've shaped the universe's structure, enabling the conditions for galaxies and ultimately us to exist. By intervening, would we be arrogantly overwriting cosmic history? Some argue that leaving them untouched is a form of reverence for the natural order, an acknowledgement that some forces are beyond human control. Others counter that exploration and manipulation are inherent to human progress. that if we can harness a black hole's energy to power interstellar travel or avert a future catastrophe, refusing to act would be its own ethical failure. The debate grows even thornier when we factor in ownership. Space law, as it stands, is wildly unprepared for this scenario. No nation or corporation can claim sovereignty over celestial bodies, but loopholes exist for resource extraction. If a black hole's energy could be mined, would it become a commodity, sparking cosmic gold rushes and territorial conflicts? History warns us what happens when powerful entities compete for scarce resources: colonialism, exploitation, war. The last thing humanity needs is to export those patterns into the galaxy. Perhaps the most unsettling question is one of unintended consequences. Black holes are still poorly understood. What if manipulating one triggers a chain reaction we can't stop? Theoretical models suggest that under extreme conditions, a black hole could emit bursts of gamma radiation or gravitational waves powerful enough to sterilize nearby space. Even a well-intentioned experiment could become a weapon of mass destruction on a galactic scale. The precautionary principle, the idea that we should avoid actions with uncertain, potentially catastrophic outcomes, might demand we keep our hands off entirely. Yet for all these risks, the potential rewards are equally staggering. A controlled black hole could offer limitless clean energy, warp drive shortcuts across the universe, or even clues to mastering quantum gravity. The same power that terrifies us could elevate civilization to heights we can't yet imagine. The choice isn't just about ethics, it's about identity. Are we caretakers of the cosmos or its engineers, passive observers or active participants in shaping the universe's destiny? This isn't a decision for physicists alone. It demands input from ethicists, policymakers, even artists' voices that can weigh the spiritual and cultural dimensions alongside the scientific ones. Because the lesson of this spinless black hole isn't just that the universe is stranger than we thought. It's that every discovery forces us to confront a deeper truth. Knowledge isn't just power. It's responsibility, and as we stand on the threshold of understanding black holes, we're also stepping into a moral frontier, one where the choices we make could echo across stars and time. This spinless black hole isn't just rewriting the rules for these cosmic anomalies, it's shaking the foundations of cosmology itself. Every galaxy we've observed, from the swirling arms of Andromeda to the elliptical giants floating in deep space, has been shaped by the gravitational dance of supermassive black holes at their cores. These behemoths don't just sit there. Their spin influences how galaxies grow, how stars are born, even how cosmic structures evolve over billions of years. But if black holes can exist without spin, everything we thought we knew about galaxy formation might need a second look. Take star formation, for example. Spinning supermassive black holes act like cosmic regulators, their jets and radiation either triggering stellar nurseries or shutting them down entirely. The energy they release carves out cavities in gas clouds, controlling where and when new stars ignite. But a non-spinning black hole, it's a silent giant, its influence far more subtle. Without those energetic jets, galaxies anchored by these still monsters might evolve differently, perhaps forming stars more evenly or retaining gas longer, creating environments unlike anything in our current models. Suddenly, the diversity of galaxies we see isn't just about mass or collisions. It could hinge on something as seemingly minor as whether their central black hole spins or not. Then there's dark matter, the invisible scaffolding of the universe. For decades, we've assumed it interacts with black holes only through gravity, silently shaping their growth from the shadows. But if this spinless anomaly hints at a deeper connection, If dark matter somehow stifles rotation or alters how black holes form, it could mean dark matter isn't just a passive bystander. It might actively sculpt the most violent objects in existence, weaving itself into the fabric of black holes in ways we've never detected. That's not just a tweak to astrophysics, it's a revolution in how we understand the universe's hidden architecture. And what about the cosmos's ultimate fate? Spinning black holes are cosmic engines, their energy influencing how galaxies collide, merge, and fade over eons. But if silent, spinless black holes are more common than we thought, the universe's long-term evolution could look radically different. Picture a future where galaxies age more quietly, their black holes emitting no dazzling jets or bursts of radiation, just cold, still gravity. The universe might dim faster, its structures evolving in ways our current simulations can't predict. It's a reminder that the cosmos doesn't just follow a single script. It's a dynamic, ever-changing story, and we've just stumbled upon a plot twist that changes everything. The most humbling part, this isn't just about one black hole. It's about realizing how much we've assumed without proof. For centuries, cosmology has been built on the idea that the universe operates by uniform rules, that what's true in our galactic neighborhood holds true everywhere. But this rebel black hole throws that certainty into doubt. What if the universe isn't uniform? What if pockets of space operate by different physics, their black holes spinning or standing still based on conditions we've yet to imagine? The implications ripple outward, touching everything from the search for alien life to the very nature of reality itself. That's the real power of an anomaly like this. It doesn't just add a new piece to the puzzle, it forces us to question whether we've been assembling the right puzzle all along. And in that uncertainty lies the thrill of discovery, the chance to see the cosmos with fresh eyes and uncover truths more profound than we ever dared to dream. The race to unravel the mystery of this spinless black hole is accelerating, with scientists around the globe drafting ambitious plans to probe its secrets. At the forefront is the Event Horizon Telescope collaboration, the same team that captured the first ever image of a black hole's shadow. They're now retooling their global array of radio telescopes to focus on this anomaly, aiming to map its surroundings with unprecedented precision. The goal, to spot subtle distortions in the fabric of space-time that might reveal whether this object truly lacks spin, or if it's hiding rotations too faint for current instruments to detect. But they're not stopping there. Plans are underway to add new telescopes in Africa and Antarctica, expanding the array's resolution until it can discern features smaller than our solar system from thousands of light years away. Meanwhile, NASA's upcoming Lynx X-ray Observatory promises to revolutionize our view of black hole dynamics. Set to launch in the next decade, Lynx will have sensitivity 100 times greater than current X-ray telescopes, allowing it to detect the faintest whispers of matter spiraling into this rebel black hole. The real game changer, its ability to measure X-ray polarization, a property of light that could reveal the hidden fingerprints of magnetic fields around the object. If magnetism is the key to its stillness, Lynx might catch the evidence in act. But perhaps the most daring proposal comes from quantum physicists, who are designing lab-based experiments to simulate black hole conditions using ultra-cold atoms and lasers. By creating microscopic black hole analogs in controlled settings, they hope to observe how spin, or its absence, affects virtual event horizons. It's like building a scale model of a hurricane to study its eye wall, except the hurricane is a cosmic singularity, and the lab is colder than deep space. Theoretical breakthroughs are equally vital. Teams are refining models of black hole formation, testing scenarios from head-on star collisions to dark matter interactions. Supercomputers like the Department of Energy's Frontier, capable of quintillions of calculations per second, are running simulations that factor in every variable, from quantum fluctuations to galactic tides, to see which recipes could bake a spinless black hole. International collaboration is the final piece of the puzzle. Projects like the Square Kilometre Array, spanning 2 continents with thousands of radio dishes, will scan the skies for similar anomalies, while the European Space Agency's Athena mission will hunt for X-ray clues. The message is clear: solving this cosmic riddle will take more than one telescope, one theory, or even one generation. But with every new tool and fresh perspective, we're not just chasing answers, we're rewriting the story of the universe itself. The black hole that refuses to spin isn't just a cosmic oddity, it's a beacon guiding us toward new frontiers in physics. From Einstein's relativity to the mysteries of dark matter, this enigma challenges us to think bigger. As we continue to explore, one thing is clear: the universe still holds secrets beyond our wildest imagination. Stay curious, keep questioning, and who knows, you might be part of the next great discovery. Don't forget to like, subscribe, and share your thoughts in the comments below. This isn't just about one black hole. It's about the bigger picture, the realization that the universe is far stranger and more wonderful than we ever imagined. Every time we think we've got it all figured out, something like this comes along and reminds us how much we still have to learn. And that's the beauty of science. It's not a destination, but a journey. A journey filled with twists, turns, and the occasional cosmic curveball that forces us to rewrite the textbooks. So what's next? The hunt for answers is already underway. Telescopes are being fine-tuned, simulations are running day and night, and theorists are scribbling equations that might one day explain the impossible. But here's the thing: you don't have to be a scientist to be part of this story. Every time you look up at the night sky and wonder, every time you share a fascinating discovery with a friend, you're adding to the collective curiosity that drives exploration forward. Who knows what we'll find in the decades to come? Maybe this spinless black hole is just the first of many, a glimpse into a hidden side of the cosmos we've barely begun to explore. Or maybe it's a one in a trillion fluke, a cosmic joke meant to keep us humble. Either way, the questions it raises are just as valuable as the answers. Because in the end, it's not just about solving mysteries, it's about discovering new ones. So keep looking up, keep asking questions, and remember, the universe isn't just out there, it's unfolding all around us, full of wonders waiting to be uncovered. Thanks for joining me on this journey, and I'll see you in the next video. Until then, stay curious.